Hi, welcome to the Olympiad geometry. Let's continue our study on radical axis. Before we start, if you think this video is helpful, please comment, click the like button, share, and subscribe the channel. Thank you. Let's see the problem. Two large equal circles intersect on x, y. Those are circle A and circle B. Two small unequal circles, circle C and circle D, intersect on PQ. Both circle C and circle D are internally tangent to circle A and externally tangent to circle B. Prove that line PQ bisects segment AB. Okay, so we want to prove that line PQ bisects segment AB. Here I do the connection of XY and AB. So we already know that circle A and circle B are equal, right? So the intersection point of XY and AB is a midpoint of segment AB, right? I mark it as M. So we want to prove that PQM are collinear. Or in other words, we want to prove that M is on the line of PQ. So what is a line of PQ? Because circle C intersects circle D on P and Q, which means that line PQ is a radical axis of circle C and circle D, right? Which means that we want to prove the midpoint of segment AB, which is M, is on the radical axis of circle C and circle D. That is saying that we just need to prove the power of M of circle C equals to the power of M of circle D, right? And we already know that circle C and circle D just unequal. And we don't know any sizing of the circle C, circle D, they're arbitrary, which means the power of midpoint M, right? Midpoint of segment AB is M. The power of M to circle C or circle D, which is internally tangent of circle A and externally tangent to circle B. The power of any of these circles should be a constant, right? The power of M to any circles that internally tangent to circle A and externally tangent to circle B should be a constant. Right, that's our guess. So let's just simplify this problem, this figure, right? Because we don't need D anymore, we just need three circles. Let's redraw it again. One circle is here. Another circle is here. And we want to have a circle that is tangent to both circles. So, okay, it just looks like this. And we know A, B here. This is XY. This is A, B, and this is M. We want to find the power of M to the circle C here, right? if we look at this figure, we already know that circle C and circle B are tangent at a point, let's call it E. And circle C and circle A are tangent to another point, let's call it F. If you look at the figure, you can feel that MEF might be on the same line, right? MEF might be collinear. So we already know that ACF are collinear and CEB are collinear. So we do the direct connection. What about MEF? Are they collinear? We don't know. Let's prove. So we want to prove 3 points are collinear. It's fairly easy, right? We just use the Mendel's theorem. So look at the triangle ABC and line MEF, right? We don't know whether they are collinear. We just use it here. So we can use, actually we're using the converse Mendel's theorem, right? So let's look at AM divided by MB. I hope you still remember the Mendel's theorem. AM divided by MB times, we want to find the production, right? AM to MB times ME to EC times CF to AF. We want to find it whether it equals to 1 or not, right? AM to MB, because M is the midpoint of AB, so AM to MB equals to 1. ME to EC, ME, sorry, here, my mistake. AM to MB and BE to EC. AM to MB, BE to EC, CF to AF, right? BE to EC, BE to EC equals to the radius of large circle to the radius of the small circle, right? CE is a radius of the circle C and BE is the radius of circle B. And CF to AF equals to the radius of the circle C to the radius of circle A, right? And we know that this production equals to 1, right? If we times these 3 equals to 1. So we know that MEF are collinear, right? MEF are collinear. Once MEF are collinear, then we know that the power of M to the circle C equals to ME times MF, right? The power of M to circle C equals to ME times MF. And we already know that circle A and circle B are equal, and M is a midpoint, which means that XY is a symmetrical line of circle A and circle B, right? They're symmetrical, which means if we extend ME, intersect circle A on a point, let's call it G, right? That MG equals to ME. So ME times MF turns out to be equals to MG times MF, right? What is MG times MF? MG times MF, that is power of M to circle A, right? mg times mf is the power of m to circle A, and it equals to mx times my. And we know that mx equals to my, so we can just write as mx squared. That is saying for any circle that internally tangent to circle A and externally tangent to circle B, they have, so for any circle have that satisfies that condition, the point m to the power of m to the any circle that internally tangent to circle A and externally tangent to circle B are equal, right? All of the power are equal, which means the power of m to circle C and circle D are equal, which means m is on the radical axis of circle C and circle D, which is line PQ, right? So PQ bisect segment AB. Okay, so this problem I think is a very interesting problem because maybe you can easily get to that we want to prove m is on the radical axis of PQ, and you get that we just need to find the power of m to C and D, but you really need to realize that we just need to find the power to either C or D, right? Because C and D are the kind of in the similar situation, because they are both internally tangent to circle A and externally tangent to circle B. So basically they are same in that way, same. And then once we find that we just need to simplify the figure, it would be straightforward that we want to prove M, E, F are collinear. And only if they are collinear, we can extend the EM to a point that intersect circle A to on the point G. So we transfer ME times MF to MG times MF and transfer it to be mx squared, right, which is a constant. Okay, I hope you like this video. See you in next one. Thank you.